Section 5 of National Geographic Magazine, Volume 1, Number 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Great Storm off the Atlantic Coast of the United States, March 11th through 14th, 1888, by Everett Hayden. In charge of the Division of Marine Meteorology, Hydrographic Office, Navy Department. Introduction. The history of a great ocean storm cannot be written with any completeness until a long interval of time has elapsed, when the meteorological observations taken on board hundreds of vessels of every nationality scattered over the broad expanse of ocean and bound, many of them, for far distant ports, can be gathered together, compared, and where observations seem discordant, rigidly analyzed and the best data selected. It is only when based upon such a foundation that the story can fully deserve the title of the history, and not romance, fact, and not hypothesis. At best, there must be wide areas where the absence of vessels will forever leave some blank pages in this history, while elsewhere, along the great highways of ocean traffic, the data are absolutely complete. Last August, a tropical hurricane of terrific violence swept in toward our coast from between Bermuda and the Bahamas, curved to the northward off Hatteras, and continued its destructive course past the Grand Banks toward northern Europe. Hundreds of reports from masters of vessels enabled us accurately to plot its track, a great parabolic curve tangent to St. Thomas, Hatteras, Cape Race, and the northern coast of Norway. 6 months later, a report forwarded by the British Meteorological Office from a vessel homeward bound from the equator indicated that it originated far to the eastward, off the coast of Africa, and only the other day the log of a ship which arrived at New York March 30th from Calcutta supplied data by means of which the storm track can be traced still more accurately, westward of the Cape Verde Islands. Not only that, but this same vessel on the 11th of March was about 500 miles to the eastward of Bermuda, and, while the great storm was raging between Hatteras and Sandy Hook, was traversing a region to the northeastward of Bermuda from which our records are as yet very incomplete. It will thus be clearly understood that while the most earnest efforts have been made not only to collect and utilize all available information, but to be careful and cautious in generalizing from the data at hand, yet this study must be considered as only preliminary to an exhaustive treatise based on more complete data than it is now possible to obtain. 4 charts have been prepared to illustrate the meteorological conditions within the area from 25 degrees to 50 degrees north latitude, 50 degrees to 85 degrees west longitude, at 7 a.m. 75th meridian time, March 11th, 12th, 13th, and 14th respectively. Data for land stations have been taken from the daily weather maps published by the U.S. Signal Service, and the set of tri-daily maps covering the period of the great storm has been invaluable for reference throughout this discussion. Marine data are from reports of marine meteorology made to this office by masters of vessels, and not only from vessels within the area charted, but from many others just beyond its limits. The refined and accurate observations taken with standard instruments at the same moment of absolute time all over the United States by the skilled observers of the Signal Service, together with those contributed to the Hydrographic Office by the voluntary cooperation of masters of vessels of every nationality, and taken with instruments compared with standards at the branch hydrographic offices immediately upon arrival in port, make it safe to say that never have the data been so complete and reliable for such a discussion at such an early date. It will not be out of place briefly to refer to certain principles of meteorology that are essential to a clear understanding of what follows. The general atmospheric movement in these latitudes is from west to east, and by far the greater proportion of all the areas of low barometer, or centers of more or less perfectly developed wind systems that traverse the United States, move along paths which cross the Great Lakes, and thence reach out over the Gulf of St. Lawrence across the Atlantic toward Iceland and northern Europe. Another very characteristic storm path may also be referred to in this connection, the curved track along which West Indian hurricanes travel up the coast. The atmospheric movement in the tropics is, generally speaking, westward, but a hurricane starting on a westward track soon curves off to the northwest and north, and then getting into the general eastward trend of the temperate zone, falls into line and moves off to the northeast, circling about the western limits of the area of high barometer, which so persistently overhangs the Azores and the great elliptical area to the southwestward. The circulation of the wind about these areas of low barometer, and the corresponding changes of temperature, are indicated graphically on the map. The isobars, or lines of equal barometric pressure, are, as a rule, somewhat circular in form, and the winds blow about and away from an area of high in a direction with the hands of a watch, in nautical parlance with the sun, toward and about low, with an opposite rotary motion, or against the hands of a watch. In front of a low there will therefore be, in extratropical latitudes, warm southeasterly winds, and behind it cold northwesterly winds, the resulting changes of temperature being shown by the isotherms, or lines of equal temperature. Moreover, in a cyclonic system of this kind, the westerly winds are generally far stronger than the easterly winds, the motion of the whole system from west to east increasing the apparent force of the former and decreasing that of the latter. Upon reaching the coast, such areas of low barometer or storm systems almost invariably develop a great increase of energy, largely due to the moisture in the atmosphere overhanging the ocean, which, when the air is chilled by contact with the cold dry air rushing in from the high, is precipitated and becomes visible in the form of clouds, with rain or snow. The latent heat liberated by the condensation of this aqueous vapor plays a most important part in the continuance of the storm's energy and, indeed, in its increase of energy. The warm light air flowing in towards the central area of the storm rises rapidly into regions where the pressure is less, that is, where the thickness, and consequently the weight, of the superincumbent atmosphere is less. It therefore rapidly expands, and such expansion would result in a much more rapid cooling and a corresponding decrease in its tendency to rise still higher, were it not for the latent heat liberated by the condensation of the moisture which it contains. Thus the forces that are conspiring to increase the energy of the storm are powerfully assisted by the presence and condensation of aqueous vapor, and the increasing updraft and rarefaction are at once marked by the decreasing barometric pressure at the center. For example, a storm was central over the Great Lakes on January 25th, with lowest barometer 29.7. The following day it was central off Nantucket, barometer 29.2, and on the 27th and 28th over the Gulf of St. Lawrence, with barometer below 28.6. But such instances are so common as to make it the rule and not the exception. As stated above, the isobars about an area of low barometer are somewhat circular in form. More strictly speaking, they are somewhat oval or elliptical in shape, and the more elongated the north and south axis of this ellipse, the greater the resulting changes of temperature, because, as it moves along its broad path toward the Atlantic, the indraft, or suction, is felt in front far down toward the tropics, and in rear far to the northward, beyond the territorial limits of the United States. Similarly, with regard to the general movement of areas of high barometer, Certain laws of motion have been clearly established by means of studies of the daily international charts. Instead of a motion toward east-northeast, these areas, when north of the 40th parallel, have in general a motion towards east-southeast, and as a rule move more rapidly and with greater momentum than lows, so that they may be said to have the right of way when the tracks of two such systems converge or intersect. These laws, or at least that relating to the Great Lakes storm track, as it may be called, soon become evident to anyone who watches the weather map from day to day, upon which are charted the systems of low and high barometer as they follow one another across the continent, bringing each its characteristic weather. March 11th, 7 a.m. The first of the accompanying weather charts indicates graphically the meteorological conditions over the wide area charted, comprising about 3,000,000 square miles, of which 1/3 is land and 2/3 water. Over the land there is a long line, or trough, of low barometer, extending from the west coast of Florida up past the eastern shore of Lake Huron, and far northward toward the southern limits of Hudson Bay. In front of this advancing line the prevailing winds are southeasterly, and the warm, moist air drawn up from southern latitudes spreads a warm wave along the coast, with generally cloudy weather and heavy rains, especially south of Hatteras. The Signal Service observer at Pensacola, for example, reports the heavy rainfall of 4.05 inches on the 10th. About midway of this trough of low barometer there is a long narrow region of light variable winds, of rapid changes in meteorological conditions, calms, shifts of wind, intervals of clearing weather, then overcast again, with cooler and fresh northwesterly winds increasing to a gale. The front line of this advancing battalion of cold northwesterly winds is more than 1,000 miles in length, and covers the whole breadth of the United States. Its right flank is on the Gulf, its left rests on the Great Lakes, or even farther north. The temperature falls rapidly at its approach, with frost far south into Louisiana and Mississippi, and heavy snow in central Kentucky and eastern Tennessee. The long swaying line is advancing toward the coast at the rate of about 600 miles a day, followed by a ridge of high barometer reaching from Texas to Dakota and Manitoba. At points along the trough, the barometer ranges from 29.70, 100 miles north of Toronto, to 29.86 at Pittsburgh, 29.88 at Augusta, and 29.94 at Cedar Keys. Along the ridge, the barometer is very high, 30.7 to the northward about Lake Winnipeg, 30.6 in Wyoming, 30.7 in Indian Territory, and 30.5 south of the Rio Grande. The difference of pressure from trough to ridge is thus measured by about an inch of mercury in the barometer. Moreover, the chart shows that there is another ridge of high barometer in advance, curving down off the coast from northern Newfoundland, where the pressure is 30.6, towards Santo Domingo, where the pressure is 30.3, and passing midway between Hatteras and Bermuda. Farther to the eastward, the concentric isobars show the presence of a storm which originated about Bermuda on the 9th, and is moving off toward Europe, where, in a few days, it may cause northwesterly gales, with snow to the northward of its track, and southeasterly gales, with rain to the southward. Storm reports from various vessels show that this storm was of hurricane violence, with heavy squalls and high seas, but it need not be referred to in this connection further than to say that it sent back a long rolling swell from northeast, felt all along the Atlantic seaboard the morning of the 11th, and quite distinct from that caused by the freshening gale from the southeast. Meteorological conditions off the coast. While this trough of low barometer, with all its attendant phenomena, is advancing rapidly eastward toward the Atlantic, and the cold wave in its train is spreading over towns, counties, and states, crossing the Great Lakes, moving up the Ohio Valley, and extending far south over the Gulf of Mexico, we may pause for a moment to consider a factor which is to play a most important part in the warfare of the elements so soon to rage with destructive violence between Hatteras and Block Island, and finally to disturb the weather of the entire North Atlantic north of the 20th parallel. The great warm ocean current called the Gulf Stream has, to most people, a more or less vague mythical existence. The words sound familiar, but the thing itself is only an abstract idea. It lacks reality, for want of any personal experience or knowledge of its characteristic effects. To the navigator of the North Atlantic, it is a reality. It has a concrete, definite existence. It is an element which enters into the calculations of his everyday life, sometimes as a friend, to help him on his course, sometimes as an enemy to endanger, harass, and delay. Briefly, the warm waters of the tropics are carried slowly and steadily westward by the broad equatorial drift current, and banked up in the Caribbean Sea and Gulf of Mexico, there to constitute the head or source of the Gulf Stream, by which the greater portion is drained off through the Straits of Florida in a comparatively narrow and swiftly moving stream. This great movement goes on unceasingly, subject, however, to certain variations which the changing seasons bring with them. As the sun advances northward in the spring, the southeast trades creep up toward and across the equator. The volume of that portion of the equatorial current which is diverted to the northward of Cape St. Roque is gradually increased, and this increase is soon felt far to the westward in the Yucatan and Florida Straits. Figures fail utterly to give even an approximate idea of the amount of heat thus conveyed from the tropics to the north temperature zone by the ceaseless pulsations of this mighty engine of oceanic circulation. To put it in some tangible shape for the mind to grasp, however, suppose we consider the amount of energy, in the form of heat, that would be liberated were this great volume of water reduced in temperature to the freezing point. Suppose again that we convert the number of heat units thus obtained into units of work, so many foot-pounds, and thence ascertaining the corresponding horsepower in order to compare it with something with which we are familiar. Considering only the portion of the Gulf Stream that flows between Cape Florida and the Great Bahama Bank, we find from the latest and most reliable data collected by the U.S. Coast and Geodetic Survey that the area of cross-section is 10.97 square miles, geographic or sea miles of 6,086 feet each, mean velocity at this time of the year 1.305 miles per hour, mean temperature 71 degrees Fahrenheit. These figures for mean velocity and temperature from surface to bottom are, it will be noticed, far below those for the surface current alone, where the velocity is often as great as 5 knots an hour and the temperature as high as 80 degrees. The indicated horsepower of a great ocean steamship, La Bourgogne, Wera, Umbria, and City of New York, for example, is from 9,000 to 16,000. That of some modern vessels of war is still greater. The Vulcan, now building for the British government, is 20,000, and the Sardegua, for the Italian government, 22,800. Again, if we convert into its equivalent horsepower the potential energy of the 270,000 cubic feet of water per second that rush down the rapids of Niagara and make their headlong plunge of 160 feet over the American and Horseshoe Falls, we get the enormous sum of 5,847,000. The Gulf Stream, however, is every hour carrying north through the Straits of Florida 14 3/10 cubic miles of water, more than 3,000 times the volume of Niagara, equivalent, considering the amount of heat it contains, from 71 degrees to 32 degrees Fahrenheit, the 3,063,000,000,000 horsepower, or more than 500,000 times as much as all of these combined. Indeed, considering only the amount of heat from 71 degrees to 50 degrees, it is still 275,000 times as great. Sweeping northward toward Hatteras with its widening torrent, its volume still further increased by new supplies drawn in from the Bahamas and the northeast coast of Cuba, its color a liquid ultramarine like the dark blue of the Mediterranean or of some deep mountain lake. It then spreads northeastward toward the Grand Banks of Newfoundland, and with decreasing velocity and lower temperature gradually merges into the general easterly drift that sets toward the shores of Europe about the 40th parallel. The cold inshore current must also be considered, because it is to great contrasts of temperature that the violence of storms is very largely due. East of Newfoundland, the Labrador current flows southward, and during the spring and summer months carries gigantic icebergs and masses of field ice into the tracks of transatlantic steamships. Upon meeting the Gulf Stream, a portion of this cold current underruns it and continues on its course at the bottom of the sea. Another portion is deflected to the southwest and flows, counter to the Gulf Stream, along the coast as far south as Hatteras. The broad features of these great ocean currents have thus been briefly outlined, and, although they are subject to considerable variation as to temperature, velocity, and limits, in response to the varying forces that act upon them, this general view must suffice for the present purpose. Now to consider for a moment some of the phenomena resulting from the presence and relative positions of these ocean currents, so far as such phenomena bear upon the great storm now under consideration. With the pilot chart of the North Atlantic Ocean for March, there was issued a supplement descriptive of waterspouts off the Atlantic coast of the United States during January and February. Additional interest and importance have been given to the facts, there grouped together and published, by their evident bearing upon the conditions that gave rise to the tremendous increase of violence attendant upon the approach of this trough of low barometer toward the coast. In it were given descriptions, in greater or less detail, of as many as 40 water spouts reported by masters of vessels during these 2 months, at various positions off the coast, from the northern coast of Cuba to the Grand Banks, and since that supplement was published, many other similar reports have been received. Moreover, it was pointed out that the conditions that gave rise to such remarkable and dangerous phenomena are due to the interaction between the warm, moist air overhanging the Gulf Stream and the cold, dry air brought over it by northwesterly winds from the coast, and from over the cold inshore current, and the greater the differences of temperature and moisture, the greater the resulting energy of action. Reports were also quoted showing that the Gulf Stream was beginning to reassert itself after a period of comparative quiescence during the winter months, and with increasing strength and volume was approaching its northern limits as the sun moved north in declination. Such then were the meteorological conditions of the coast, awaiting the attack of the advance guard of this long line of cold northwesterly gales, conditions still further intensified by the freshening gale that sprung up from the southeast at its approach, drawing reinforcements of warm, moist ocean air from far down within the tropics. The energy developed when storm systems of only ordinary character and severity reached the Atlantic on their eastward march toward northern Europe is well known, and need not be referred to further. Let us now return to the consideration of this storm, which is advancing toward the coast at the rate of about 600 miles a day, in the form of a great arched squall, whose front is more than 1,000 miles in length, and which is followed, far down the line, by northwesterly gales and temperatures below the freezing point. End of section 5.